So very good day to everybody. Once again, this is machine learning, and in this class we discuss about information search, about the ranked learning, and of course the topic modeling. Okay, so this is especially for you, my dear students and young researchers, and you can reach me at dr.christoananth@gmail.com. So before beginning the session, once again let me thank God for giving me this opportunity to deliver this useful session to share my knowledge among my fellow national, international participants, students, and young researchers. Right. So in this class, we have a short introduction towards ranking, how you try to make the ranking about the applications, what are the evaluation metrics about the ranking. Okay. Then we discuss about MAP, M-A-P, mean average precision. Okay. Then we discuss about discounted cumulative gain, DCG, and what are the machine learning models that you will be using for learning to rank. Okay. What are the point wise methods? Okay, so that we'll be discussing. Okay, what will be the BC loss? Okay, in the pairwise methods as in the rank net method. Okay, then we try to summarize all the list-wise methods. Okay, what is the uncertainty in the scores in order to produce a smooth loss in the soft rank. Okay, then finally we will have the probability of various permutation using Plackett-Luce model in the listnet. Okay, so that we'll be discussing. Okay, so at regular intervals I'll be giving you some short videos to discuss the knowledge in our topics. Right. So ranking, if you can see, okay, you are going to analyze the data and you have to identify, okay, which is the topmost one according to the similar images. Okay, so if you take in the case of retrieving the information, okay, so maybe you can use it maybe in the search engine also, like Google search engine. Okay, like if we have a user profile, like maybe location, age, gender. Okay, you can go with the textual query. Okay, you can sort the web pages, you can arrange the web pages according to the relevance. Okay, or you can also have recommender systems also. For example, you take in the case of Amazon. Okay, you are ordering some product. Okay, you are ordering fridge. Okay, you are searching for fridge. Okay, immediately it will show fridge plus washing machine is this one, this price. So immediately you will see that. Okay, so that's a recommender system. Okay, so you have the user profile, you have the purchase history, and you can actually sort the other items in order to find out the potentially interesting products. Okay, then travel agencies. Okay, for example, if we are booking a flight, okay, from the capital city Tashkent, okay, to any other place, then next day the price is less, you want to book, it will ask. So for example, if you are booking a hotel, you are making a railway reservation, so it will be showing you the check-in dates, check-out dates, the number, age of travelers, everything it will be sorting. Okay, the available rooms according to the relevance. Okay, so this is the ranking applications. If you take in the case of machine learning, you can actually search. Okay, in Amazon also you can go with the similarity search even. Okay, so top watches just for you, or maybe you are booking a flight ticket. Okay, Switzerland. Okay, from March 3 to March 4, travelers, one room, 3 travelers, so that you can go with the similarity and ranking applications even. Okay, so we predict these ranking models. Okay, so that according to the relevance score we will be calculating. Okay, so S is equal to f of x for each of the input value x. Okay, so here you will be having query and then document. Okay, so q is the query and d is the document. Okay, so once we have the relevance of each of the document, we can rank the documents according to the scores. Okay, so x is equal to query comma document, so it will pass to the scoring model. Here you will be having S is equal to f of x. Okay, so here the scoring model you can implement it using several approaches. Maybe you can use for vector space models. Okay, so that's a vector embedded approach where you can use term frequency, inverse document frequency, or maybe bidirectional encoder representation from the transformer, so that you will be using for the query and then document, and from this one you will be computing the relevance score. Okay, so f of x is equal to f of q comma d. Okay, as we have the cosine similarity between the vector embedding of the query and then the document. So this is about learning to rank. Okay, so we will have the scoring model, so that's a ML model, machine learning model, that you will be learning to actually predict a score. Okay, so here the x input is nothing but the q comma d. Okay, query and then the document. Okay, so where the ranking loss that you can actually minimize it. Okay, and you can also go with ranking evaluation matrix as well, where you define the matrix in order to evaluate the ranking models. Okay, so these metrics you can compute based on this predicted document ranking. Okay, maybe like kth order top retrieved document that you will go with. Okay, so that will be having the predicted score of yes. Okay. So this is the mean average precision map, that's map. Okay, so according to the yk value, okay, 1 0 1 1 0 1, okay, like first, second, third, fourth, fifth and sixth, we will be calculating the probability and the rank. Okay, so this is 1, okay, 0 0.5 0 0.67 0 0.75. So from this one you will be calculating the average precision. So average precision from this probability and the ranking, you will be calculating it as 0.77. Okay, so from this one value 0.5 0.67, so here we are actually going on with a graph with a precision and then recall. Okay, and the formula for calculating the access precision would be summation k equal to 1 to n rk minus 1 multiplied by probability k. Okay. So mean average precision, you can use it for the tasks, especially with the binary relevance. Okay, so when the true score y of the document d can only be 0, which is non-relevant, or maybe 1, which is actually relevant. So either binary thing will be there. 1 means relevant, 0 means non-relevant. Okay, so accordingly we will be calculating the corresponding documents d is equal to d1 up to dn. Okay, we can check how many of the top k retrieved documents are actually relevant. So relevant means 1, non-relevant means 0. Okay, in order to compute the precision pk, okay, and recall rk. Okay, so for k equal to 1 to n, we try to get the different value, okay, pk and then rk value, that you will be having the precision recall curve. Okay, so this area under the curve you can call it as the average precision. Okay, so if you compute the average precision, that mean of the values, so you will be getting the mean average precision. So this is the thing, first, second, third, fourth, fifth and sixth. Okay, so this one, okay, it is yes, yes, no, half. Okay, so that is the thing. Okay, 0 1. Okay, so anything over 3 and 4 it is good. Okay, 0 1 very low. Okay, so that you will be categorizing, okay, with the case of discounted cumulative gain. Okay, so here you will be having yk, gk and then dk. Okay, discounted cumulative gain. Okay, normalized discounted cumulative gain, so that you will be categorizing. Okay, so from the gk, from the gain value, it is 2 yk minus 1. Okay, and the dk discounted value 1 by log 2 of k plus 1. Okay, so the discounted cumulative gain is equal to gk multiplied by dk. Okay, so that is how you will go with the n, dcg and so on. Discounted cumulative gain, normalized value, normalized value of the discounted cumulative gain. Okay, so actually normalized is nothing but you are finding out the average out of this, right? So discounted cumulative gain, especially you can use it for the tasks, okay, with the graded relevance. Okay, when the true score y of the document d, it's actually a discrete value, so maybe you can have a scale. Maybe 0 means bad, 1 means okay, 2 means good, 3 means excellent, 4 means perfect. You can have just as you see here. Okay, 3 4 good, 1 down, 2 okay, elik, okay, 0 yamon, okay, 1 yamon. Okay, so that you will be having the values. Okay, so that's a grade. So for the given query q and then the documents d, okay, so you'll have d1 to d1. Okay, we will be considering the kth top retrieved document. Okay, so gk is equal to 2 power yk minus 1. So that is actually from the formula you will be having. Okay, and the discount dk is equal to 1 by log of k plus 1. Okay, so the sum of the discounted gains. Okay, so you will be having discounted cumulative gain, that is dcg, for the kth value of 1 to n. And this is the IDCG, okay, ideal score. Okay, so when the score is between like 0 to 1, okay, we can divide this measured discounted cumulative gain by the ideal score, IDCG. Okay, so that you will be having normalized discounted cumulative gain, that is what we calculated, NDCG. So NDCG is equal to discounted cumulative gain divided by ideal score discounted cumulative gain. So DCG by IDCG. Okay. So from the product P1, P2, P3, P4 and P5, you will be having relevancy 0, 2, 1, 2 and 0. So this one 0. Okay. So this one 1. This is 2. The system will go with recommendation. So that is the where in Amazon and all, so it is completely very much relevant. So it will be showing. Okay, so this is the relevant product for you. You want to buy it or not, it will be showing. So in order to build this machine learning model, okay, for the ranking, okay, we have to define inputs, outputs and the loss function. Okay, so for this one, yeah. So for the query queue, we will have n number of documents. So D is equal to D1 up to Dn. That will be ranked according to the relevance. Okay. So here you will be finding out xi, okay, q, okay, query, and then document di, which are nothing but the inputs to our model. So here we will be computing the output for the query document. Okay. So input xi is equal to q comma di. Okay. So we will be existing a true relevance score yi. Okay, so you will be calculating the output yi. Okay, so our model will be outputting the predicted score. Okay, so si is equal to function of xi. Okay, so here you will be using the base machine learning model. Okay, so decision tree or maybe neural network to compute the s is equal to fs. Right, so we'll go with the choice of the loss function. You have to find out input, the loss function, and of course the output. And for the case of loss function, okay, there are three approaches on how the loss can be computed. Okay, so we'll go with the point wise method. Okay, so that you'll be finding out the total loss. Okay, so that will be the loss that is associated with the each of the document. Okay, di. Okay, so that is the point wise method that we will be calculating as the distance between the predicted score si and the ground truth yi. Okay, so we can actually transform, okay, especially in the regression problem, okay, where you are going to train the model in order to predict the y. Okay, then you will go with pairwise method. Okay, so you will compute the loss terms, especially for the each of the pair of the documents di and then dj. Okay, so similar to the point wise, we will have pair, okay, like di and then dj, okay, for I and j equal to 1 to n. Okay. So here you will be having the point wise method. Okay, you are going to predict whether this yi is greater than yj or maybe yi is less than yj. Okay, which of the two documents are actually relevant. Okay, so here you will have, actually go with the binary classification problems in order to find out, okay, whether it is relevant or not. Okay, so that one you can also go with the list-wise methods even. Okay, so that according to the list of the documents, you can calculate the ranking metrics that is incorporated for each of the loss. Okay, so this is the machine learning approaches. Okay, that you can use it for the learning to rank point wise, pair wise, and then list wise. Okay, so here you will be having query q and then document d. Okay, so this is from di to dn. Okay, so the point wise method you will be having input the single candidate, so x is equal to query comma document. Okay, and you will be calculating how accurate especially is the predicted score. So si is equal to yi, whether it is equal. Okay, how it is accurate, and the solution would be you can go with a regression analysis. Okay, in transforming the task as well. Okay, then the pairwise method you will be having pair of candidates like xi and then xj. So q di, q di. Okay, so that both the things you will be having pairwise, and you will be calculating the loss whether yi is greater than yj or maybe yi is less than yj. Okay, so in this case, if yi is greater than yj, then you will be having the predicted score si is greater than st. Okay, so that you will be calculating, and here the solution would be binary classification. Then the list wise candidates, you will be having whole list of candidates. So x1 is equal to q comma d1 and up to xn is equal to q comma dn. Now you are going to take into account all the retrieved documents. Okay, and you will be having discounted cumulative gain for the loss as well. So this is the point wise approach. It's very much easy. Okay, and of course it's the first to be specialized for the ranking tasks as well. Okay, so between the ground truth score yi and the predicted si score, predicted score si, we are actually using the regression analysis, okay, in order to go with the point-wise method, okay. So for this one, we will be calculating the MSE, mean square error loss, okay. So that one, the loss S comma Y is equal to summation I equal to 1 to n Si minus Yi the whole square. So that you will be calculating the mean square error. So the major disadvantage is that with the case of point-wise method, okay, the true relevance score are actually needed in order to train that model, okay. So that is the reason even like pairwise methods also, it will not be working in relevance, okay, that is the thing, okay. So they work in relative preference, which means that if there are two documents, we want to predict if the first is more relevant than the second, okay. So maybe we can use the binary classification method where you can go with the ground truth like Yij, okay, which is equal to 1 if Yi is greater than Yj, okay, or maybe 0 otherwise, okay, and we try to map the models, okay. So Sij is equal to sigma, okay, the standard deviation Si minus Sj, okay. Then we will be having the binary cross entropy loss, okay. So Ly is equal to summation I and then j equal to 1 to n Yij log Sij, okay, plus 1 minus Yij log of 1 minus Sij, okay. So here you will be using ranking net methods, okay. So that will be an enhancement, an advantage over the point-wise method, but still every documents are given equal importance, okay, during the training, but still you have to identify which is having the higher rank, okay. So ranking information is definitely important because we can actually sort, you can actually align, okay, and of course sorting it's non-differentiable, okay. So that is the reason you can go with gradient design optimization, okay. Especially we don't need a loss function, we just have to have a gradient in order to calculate this gradient design optimization. So this is the lambda rank, okay. So that will be calculating the implicit loss function, okay, which means that documents with higher rank will be having higher gradient, okay. So lambda j is equal to dou L by dou Sj equal to 1 by G max, okay. So that is the gamma value. So summation I not equal to j, standard deviation of Si minus Sj, okay, with the Gi minus Gj and then Di minus Dj. So here more than lambda rank, you can go with the lambda mart as well. So that will be giving better results than the lambda rank. And then with the case of list-wise method, okay, as the name implies, it's a list, everything is displayed as a list, okay, and you are finding out the relevance, okay. So point wise as well as pair wise approaches, they generally transform this ranking problem, okay, maybe like a regression task or maybe binary classification task even, okay. List methods, you can solve the problem more directly, you can actually maximize this evaluation matrix, okay, and you can set the loss function. So 1 minus normalized discounted cumulative gain. So that will be the rank information that is needed to compute the discount decay. So that you can actually go with the predicted score and maybe it's not differentiable as well. Okay. So maybe you can either use lambda rank also or maybe an advanced method like lambda mart also that you can use them. So that would be an advantage over the pairwise as well as list-wise based approaches. So next one, you can also go with soft rank, okay. So that earlier cases it is non-differentiable, but this one it's a differentiable. You can actually go with the smoothened probabilistic score, okay. So S is equal to n of f of x, okay, summation the variance, okay, sigma square. So that you will be having the probability distribution function, okay. So using this soft normalized discounted cumulative gain, you can actually provide a smooth function, okay, over the all the previous methods that you will be obtaining. So this is the uncertainty in this course, which is actually providing the smooth loss, okay, deterministic smoothen with respect to the score, okay. So that will be producing according to the different, okay, probabilities, okay, P of S, okay. So with regards to the score, okay. So rank 1, rank 2, rank 3, that you will be obtaining, okay, for the deterministic and then for the smoothen as well. Then finally you will go with the Plackett-Luce model, okay. So that is especially with the case of permutation, you can actually define the loss, okay, over the space of permutations, and you can use listnet function, okay, where you will have the list of scores and we define the probability of the permutation. Okay, so that is the reason you go with BCE distance, binary cross entropy distance, between the true and the predicted probability distributions as well for the given space of permutations. Okay, so this is the Plackett-Luce model. So this is the equation P of pi by S. Okay, summation. This is actually pi of E of S of pi I divided by summation K is equal to I to N e power S pi K. Okay, so here you will be calculating the probability function SB, SC and SA. Okay, you will be having ESB divided by ESA plus ESB plus ESC. So that you will be calculating, and corresponding to each of the sides, okay, SA, SB and SC, you will be having the function with respect to y. Okay, so that is nothing but the probability of the various permutation using this Plackett-Luce model.